Hey guys, Ms. Peterson here, and welcome to AP Physics 2, Lecture 4-2, all about resistor-only circuits. So we're going to be talking about resistors both in series and in parallel, and how to calculate the equivalent resistance of those types of circuits. So first off, as we start to go through our circuits more and more, we're going to be drawing lots of circuit diagrams, and there's some standard symbols that we use that you'll typically see. We got the battery, the switches, wires is of course just a line, ammeters and voltmeters, capacitors, resistors, and bulbs are the ones that we'll be using most often, these over here. These ones over here are a little beyond the scope of the class, but if you look up a circuit diagram for anything that you have, you might see them, so figured I'd show you what they are. Now, there are two words that we use for wiring things. So when things are wired along the same path of a wire, we say they're wired in series, while elements that are wired in parallel will have a junction, okay? It'll have a split in that wire, in that current, before or after them, okay? So let's look at some examples, okay? Right here, we see this is the battery, we have a switch, and then we have 3 light bulbs. We have 1 light bulb in parallel with these 2 light bulbs that are in series with each other, okay? So 1 light bulb in parallel with 2 light bulbs that are in series with each other. What about this one? Okay, well, we still have our battery and switch. So we still got our battery and switch. And then these squiggly lines are resistors. So these are 2 resistors in parallel. Yep. And then let's go ahead and draw one. So we have a battery, an open switch, and 1 bulb in series with 2 resistors in parallel. And then we're going to add our voltmeter and ammeter. Okay, so let's go ahead and first add in our battery. And then we'll have our open switch. And then we have 1 bulb. Okay, so I'm going to go ahead and do my bulb that is in series with 2 resistors in parallel. So there's one of those resistors in series with that bulb, but it is in parallel with another resistor. Okay, so these 2 resistors here are in parallel with this light bulb, and they're in series with that whole thing. Okay, now if I wanted to add an ammeter and a voltmeter, we have to know how those are added. So ammeters are always added in series. So we would just pick somewhere on our circuit and add an ammeter, okay? Where voltmeters go in parallel. So say I wanted to do the voltage across this resistor, I could do something like that to get the voltage drop across the resistor. I could also do a voltmeter here and get the voltage drop across the bulb, okay? Or connected across this resistor, okay? Okay, cool. So how things are wired, of course, affects the behavior of the circuit. So first, let's talk about series circuits. Now, in a simple series circuit, there is only 1 path for current, okay? So the current that is flowing through the circuit, okay, we draw it from negative or from positive to negative in the battery, the direction of that positive charge flow, okay? But if we're thinking of the current as that charge over time or the flow of the charge, well, there's only one way for it to flow. And so it's not going to change anywhere in the circuit, okay? That's the law of conservation of charge, okay? That charge, the energy is going to be used by the resistor, but the charge itself is going to flow through the whole circuit, giving some of its energy to each element. So the current will be the same everywhere. Okay, so yeah, I total equals, it would be like if this would be the current going through the 5 ohm resistor would equal the current going through the 10 ohm resistor, okay? It would all be the same. Okay. Now, if we were thinking about the energy used in the circuit, where we get 10 volts per coulomb, okay, that energy per charge given by the battery, and then it's going to have to be shared among these 3 resistors, okay? So just to give you like a quick example of a series circuit here and how we would solve it is we would have that 10 volts, and then in this one, because the current has to travel through each individual resistor, okay, the total resistance is going to be 20 ohms. Okay, so our total is going to be 20 ohms. And that comes from 5 plus 5 plus 10, adding up each individual resistor. Okay, so now remember V equals IR, Ohm's law. We can find the current in the circuit by doing the voltage, the total voltage, 10 volts, divided by the total resistance, 20 ohms. Okay, current equals that voltage over the resistance. So we get 0.5 amps of current. So we will have 0.5 amps of current flowing everywhere in this circuit. Okay. Now, by the law of conservation of energy, the voltages drops across each of these have to add up to that voltage of the battery. Okay, they have to all be equal. So I'm going to go ahead and write that real quick. So the voltage of the battery equals the voltage of lost in resistor 1. Oh, I'll be specific. The voltage of the 5 ohm resistor times the voltage of the 5 ohm resistor plus the voltage of the 10 ohm resistor. Okay, so using V equals IR, we could also write that, and we would get that the voltage of the battery is that total current times the total resistance. And then we have I times the 5 ohm plus I times the 5 ohm plus I times the 10 ohm. Okay, so hopefully you guys can see how that current all cancels out. And then we get that the R total, the equivalent resistance, is 5 ohms plus 5 ohms plus 10 ohms to give us that 20. And that's how we add resistors in series. Okay, so, and that is how we calculate that total resistance. R total is just going to be R1 plus R2 plus R3, etc., etc. On your equation sheet, how that's represented is that R series, so that's the equivalent resistance of resistance in series, equals the sum of each individual resistance. Okay, sum of individual resistors. Okay, so the effect of that is that when we're in series and we keep on adding resistors, we increase that total resistance. Okay, where parallel circuits are a little different. Okay, in a parallel circuit, if we're looking at this, okay, each resistor is in a loop connected directly to the battery. If you remember that know your potential type thing, this whole wire is all connected. Okay, so it's all going to be at 10 volts. Well, this is all connected to the negative terminal of the battery. So it's all going to be 0 volts. Okay, so the voltage drop across each resistor will be the same. They are all going to be that 10 volts. Okay. Now, the effect of that, okay, we got that resistance, we got the total, okay, we can find the current. Remember, current equals voltage over resistance. So through this one path, we have 10 divided by 5, or 2 amps of current. This amp, we will also have 2 amps of current. And through this one, we will have 10 divided by 10, or 1 amp of current, which makes sense, okay? If you have more resistance, you're going to have less current flowing, okay? It's going to be slower. It's going to back up and have more repulsions there as it travels through the circuit. But then these currents are all going to come together, okay? 2 plus 2 plus 1, and we have 5 amps of total current being pulled from the battery. And then it splits per the junction rule and feeds all of those, okay? So here, how would we calculate the total resistance? Okay, if we have more paths open, that lowers the total resistance, okay, because each of them need to pull that current, so they're going to pull that current and increase that, and you open up more paths, so there's more options for where that current flows, which minimizes the repulsions and lowers that total resistance, okay? And here, okay, it's not the voltages that all add up to the battery voltage, but rather you can think of it as the currents all add up to the total current flowing through the battery. So if we look at it from that perspective, okay, I'm going to go ahead and do this in red. Okay, we would have the total current, that 5 amps, equals the current through path through the 5 ohm resistor plus the current through that other 5 ohm resistor plus the current through the 10 ohm resistor. But then we want to write it in terms of the resistance and figure out how to calculate that total resistance. Okay, this makes sense. Law of conservation of charge. So now I'm going to write it in terms of the voltage and the resistors. So current is voltage over resistance. So we have delta V of the battery over the total resistance equals delta V over the 5 ohm plus delta V over the 5 ohm plus delta V over the 10 ohm. Okay, and since all of those voltage drops are the same, we can cancel them all out. And so we get our equation for calculating total resistance in parallel as 1 over R total equals 1 over R1 plus 1 over R2 plus 1 over R3, etc., etc. Okay, so on your equation sheet, how that's represented is that the equivalent resistance of parallel resistors equals the sum of 1 over the individual, 1 over the equivalent resistance in parallel equals the sum of 1 over the individual resistors. Okay, and that makes sense too. You can look at that here through that total resistance, easy. Okay, we have 10 volts divided by 5 amps, which gives us our total of 2 ohms. Okay, you could also find that by doing 1/5 plus 1/5 plus 1/10 and taking the inverse of that. Okay, now we're going to go ahead and summarize everything in this summary chart. Okay, so let's go ahead and draw those in. Okay, series, I'm just going to do it with 3 resistors to make it easy. So we got the series versus the parallel. Okay, and let's go ahead and look at it in a simulation because that might kind of help you guys make sense of this. So this is my FET simulation. This is the FET circuit builder. I have a series circuit here with 2 light bulbs. As you can see, I can close the switch on that and we get 0.45 amps of current going through the 2 10 ohm ones. Now, if I break that circuit and add in another light bulb so we have more resistance, we can see our current decreases. We have less total current. Okay, each of these got less bright. They're getting less voltage, less energy, so less power. And we have that relationship. Okay, so let's summarize that for series. The voltage is split. Okay, the voltage is split. So you can always say that the voltage of the battery will equal the voltage of R1 plus VR2 plus VR3. And let's be specific. The voltage changes. The voltage drops. Okay, where in a parallel circuit, they are all the same. Okay, so the voltage drop across the battery will equal the voltage drop across R1, will equal the voltage drop across R2. That's an equals, not a plus. Will equal the voltage drop across R3. Okay. Now for current, okay, as we just saw, it's the same everywhere in a series circuit, and it decreases as you add elements. Okay, so the total current will equal the current through each resistor. Okay, where in a parallel, the current is split. Okay, but because it splits through the different path, it will increase as you add elements. Okay, so I total equals I through R1 plus I through R2 plus I through R3. Okay. And then for resistance, here the resistance will always add, okay, directly, where this one, it will do that inverse. So 1 over the R total equals 1 over R1 plus 1 over R2 plus 1 over R3. And again, that will also, it will decrease as you add elements. Where in series, it will increase as you add elements. Okay, so for resistance, increases when you add elements. Where for parallel circuits, the equivalent resistance will decrease as you add elements. Okay, so let's go ahead and look at the parallel circuit in that simulation. So in the parallel one, okay, right here, let me go ahead and close that switch, and we can see automatically they're much more bright than they were in either of the two series circuits. We have more current going, and if I add another path, okay, that bulb is going to be just as bright and pull more current and increase that total current in the circuit. So you can see the difference between the series and the parallel. One other cool thing about series and parallel to know is that in a series circuit, if I were to break the circuit at any point, so say like this light bulb goes out, okay, that will break the whole circuit because now we don't have a loop for the current to flow. Where in a parallel circuit, okay, if I were to break this light bulb, there's still full loops for the current to flow, so it will not affect the other circuit elements. Okay, cool. Okay, cool. Let's do some examples. So let's do some practice with a simple series circuit. Okay, we have some 5 kilo ohm resistors. So the units of my resistance is going to be kilo ohms, okay, which is times 10 to the third ohms. So we have R1 is 3, R2 is 10, and R3 is 5. Okay. And then we have a 9-volt battery, so 9 volts coming from the battery. It is a series circuit, so what's going to be the easiest for us to find? Okay, it's going to be the total resistance because we can just add them up. So we got 3 plus 10 plus 5 for 18 kilo ohms total. Okay, now if we know the total resistance, we can find the current in the circuit. So I have 9 volts divided by 18 times 10 to the third ohms. Okay, 9 divided by 18 is 0.5. So I have 0.5, 10 to the third is on the bottom. So if we moved it to the top, it'd be 10 to the minus 3, which we normally just call milli. So I'm going to do my current in milliamps. Okay, if you do milliamps in kilo ohms, they end up canceling out. So we can just do that voltage directly. So it would be 0.5 milliamps. So what's next? Well, it's a series circuit. So that current is going to be the same everywhere. There's nowhere else for it to go. So it's going to be 0.5 amps around every part of that circuit. Okay. So hopefully then you can see we can just use V equals IR to calculate that voltage. The times 10 to the minus 3 from the milli and times 10 to the positive 3 from the kilo will cancel out, okay, when we multiply them. Negative 3 plus 3 is 0. So we can just multiply them directly, which means that we'll have 1.5 volts across R1, okay, and 5 volts across R2, and 0.5 times 5, 2.5 volts across R3. And we can always check 1.5 plus 5, that's 6.5, plus 2.5, that's 7, 8, 9. 9 volts total. Okay, so we have solved out the circuit. We can also solve out the power. Remember, power in a circuit is current times voltage. It's related to the brightness of the bulbs, or in this one, it would be the rate of the heat dissipated off of those. And yet it is in units of, what is the unit of power? What? Watt is the unit of power, okay? Watt. So if we're doing current times voltage, though, we're actually going to be in milliwatts, okay? Or times 10 to the negative 3 watts, because we got the milli in the current. So 1.5 times 5 is 1.5 times 0.5 is 0.75. Okay, and then we got 5 times 0.5, which is 2.5 watts, milliwatts. 2.5 times 0.5 gives us 1.25 milliwatts. So the total power rating of this circuit would be 4.5 milliwatts. Okay, cool. Oh, and just for fun, power is how light bulbs are rated. So they have a power rating. So whatever voltage you apply, that tells you how much current it'll draw from the wall or whatever it's pulling from. Okay. Let's go ahead and try a parallel circuit. Okay. Now, again, the hardest things in these are really going to be just figuring out what is the easiest thing to solve next. Okay. So for parallel circuits, go ahead and draw in the things that we know. We know this is 9 volts, and then we have the 10 kilo ohms, and the 2 kilo ohms, and the 1 kilo ohm. Yeah, okay. We can't find the total. I mean, we could find the total resistance. We could do 1 over R total equals 1 over 10 plus 1 over 2 plus 1 over 1. Okay. But an easier way to do it, I think, is to actually do those voltages and the currents first. Okay. Because we know they're in parallel, they're all going to have a 9 volt drop across them. Okay. So we can use V equals IR to calculate their current in milliamps. Okay. Current will be the voltage divided by the resistance. So we have 0.9 amps there. Okay. Again, current equals voltage divided by resistance. 9 divided by 2, 4.5 amps going through that resistor. 9 divided by 1, 9 milliamps going through that resistor. For a total of 14.4 milliamps of current in our circuit. So then we can find our total resistance. Okay. Our total would just be our resistance equals the voltage drop divided by the current. So we got 9 divided by 14.4, which gives us 0.64 kilo ohms. Okay, and I do like to check that. Let's go ahead and check it. 1 over R total equals 1 over 10 plus 1 over 2 plus 1 over 1, so 1. So 1 plus 1 over 2 plus 1 over 10. And then I take the inverse of that. And what do you know? I get 0.63. So a little off, but that's probably just due to rounding issues. Okay. So then we can do power as our last step. Okay. Power equals voltage times current. So, and this will be in not watts. I actually want it in milliwatts, so we don't have to convert that current. 9 times 0.9 gives us 8.1 milliwatts through being pulled by R1. 9 times 4.5, we got 40.5 milliwatts of power coming through R2. And 9 times 9, 81 milliamps of power coming from R3 for a total power of, just adding them all up, 129.2. Okay, about 130. Did I do 9 divided by 14.4 right? No. When I do 9 divided by 14.4, I get the right answer, the exact same answer that I get from that. Okay, yeah, this is 0.625. Okay, I don't know what I did last time. I think I used 10. Okay, cool. Oh, and then does that match the power too? If we did current times voltage, 9 times 14.4? Yeah, 129.2. Okay, cool. Okay, cool. Moving on to the last one, which is complex circuits. Okay, now combined circuits are challenging because basically you have to make them simple. So you have to combine elements into equivalent resistances until they become simple. So let me go ahead and show you how we do that with this big ol' example problem. Okay, I'll go ahead and add in my resistances. We have some of these are in ohms and some of them are in kilo ohms. I'm going to go ahead and just convert them all to kilo ohms to make it easier on us. So resistance in kilo ohms. So 330 would be 0.33 kilo ohms. And then we have 3.3 for R2, 10 times that resistance. 8.2 kilo ohms for R3. 4.7 for R4. And 10 for R5. We have the voltage of the battery, which is 9 volts, okay? And then that's all we know right now. So our first step is going to be to simplify the circuits and combine what we can combine. So when we're combining them, we're going to start from the outside in. So I'm going to start by combining these two resistors that are in series with each other. And I'm going to redraw the circuit so that it makes more sense to us. We still got that 9-volt battery. We still have R1, which is 330 ohms. But now, still got R5, 10 kilo ohms. Okay. And still got R4, which is 4.7 kilo ohms. Okay, but these two, R2 and 3, I'm going to combine, okay, and treat them, R2 and 3, as one resistor with a resistance of 8.2 plus 3.3. So 8.2 plus 3.3, I should be able to do that in my head, but I'm tired and it's Friday. 11.5 ohms. Okay, kilo ohms to be, don't want to mess up my units. Okay, 11.5 kilo ohms. Okay, now we're almost at a simple circuit. Now we have this in series with these two that are in parallel with each other. So I'm going to go one more step and combine these two resistors to make a simple series circuit. Okay, so if I go ahead and go, we got the 9 volts there. We have R1, which is 330 ohms. And we still have R5, which is 10 kilo ohms. And now this is going to be our 2, 3, and 4. But since these are in parallel, I can't just add them directly. Okay, I'm going to have to do 1 over that equivalent resistance. So that'll be our R234 equals 1 over 11.5, the R2 plus 3 plus 1 over 4.7. So when we solve that out and do the algebra, okay, we have 1 over 11.5 plus 1 over 4.7. And then I take the inverse of that to get 3.34. Okay, 3.336. So I'm going to go ahead and say 3.34 kiloohms. Okay. And now, okay, if you look at this circuit right here, it is a simple circuit. All we have is 3 resistors in series, which makes it easier for us to solve. Okay, so let's go ahead and do that. First, I'm going to go ahead and find that total resistance. So I have 330, so 0.330 plus 3.34 plus 10 for a total resistance. Again, I'm just adding them directly because now they are all in series with each other. So that equivalent resistance is 13.67. So I'm just going to round it and say 13.7 ohms. Okay, so 13.7 ohms is our total resistance. Okay. So we can use that to solve for the current in this circuit. Okay, so we're going to solve for the current in this circuit. Okay, and that will be the total current. So it'll equal 9 volts divided by that total resistance, 13.7 kiloohms. Okay, so 9 divided by 13.7 gives us 0.656. So 0.657, and it's divided by kilo, so it'll be milliamps. Okay, again, if you got the kilo on the bottom, that's 10 to the third. So this is times 10 to the minus 3 when it goes up top. Okay. So that will be the current passing through R1, R234, which isn't one of our resistors, and R5, but definitely R1 and R5. So we can add that to our chart. Okay. So through R1, 0.657 milliamps. Okay. Again, I'm doing the current in milliamps. 0.657 through R1 and 0.657 through R2. Okay. Which, as you can hopefully see, allows us to calculate those voltage drops across the current and the resistance. Oh yeah, and that's the total current, 657. Okay. So we can calculate those. We have a milli times kilo, so that cancels out. So 6.657 times 10 gives us 6.57 volts there, and 0.657 times 0.33 gives us 0.2168. So I'll go 0. Most of our resistances only have 2 sig figs. I'm going to round this to 2 sig figs for this one and say 6.6 volts there and 0.22 volts there. Okay. So I'm going to add that information to our pictures. Okay. So we'll have a delta V of 0.22 there. And for that 10 ohm, 6.6. Okay. Now I could also find that voltage drop then across the R23. Okay, the delta V there would be the current. So 0.657, carries some extra while calculating, times 3.34 gives us delta drop of about 2.2 volts, which makes sense because if I do 9 minus 6.6 minus 0.22, I get 2.18 or 2.2. So that voltage drop is 2.2. And that's at this point and this point in the circuit, after R1 and before R5. So that will equal that voltage drop across R23 and across R4. Okay, so we know the voltage drop across R4 then is going to be that 2.2 volts. Okay, so R4 has 2.2 volts. And then we know the R2 plus the R3 drops will have to add up to that 2.2. But I haven't figured that out yet, so let's just keep on going. Okay, so the current then in that path, okay, we can find the current flowing through that resistor. Okay, V equals IR, so I have 2.2 divided by 4.7 to give me 0.47 milliamps, 0.468. I'll keep on carrying the extra sig fig there. Okay, so we have about 0.47 milliamps going through that one. Now, if we're looking at this circuit, okay, the second one that we've created, and we just calculated that we have 0.468 amps going that way. And we had already calculated that we had 0.657 amps there. So, junction rule, we know the current going in and the current coming out that way. We can find the current going down this path. Okay, the current going down that path will just be the differences in those currents. So I have 0.657 minus 0.468, which gives us 0.1889 or 0.19 amps. Okay. So that is how much current is flowing through this path. Okay. 0.19 amps. And again, we found that by this minus that. 0.657 minus 0.468 gives us 0.189. So why am I doing? I'll be consistent in my sig figs. So as you can see, now we have enough information to calculate those voltage drops across those. So 3.3 times 0.189 gives us a voltage drop here of 0.62, and 8.2 times 0.189 gives us 1.554. We'll go 1.5. And of course, I like to check and make sure that these two voltage drops should add up to 2.2. And indeed they do. Okay. So then power rating, okay. Power, remember, is current times voltage. I will quickly do those calculations for you. So you can check your answer, and this will be in milliwatts again. Yep. So we got all those numbers, and we can add them all up. To get our total power rating of our circuit of about 5.9 watts, almost 6 watts. And you can always check that the voltage times the current equals that total power, which again can be found from the sum of the power of the individual resistors, or using voltage times current with the total voltage and individual one. Okay, and that's how we solve complex circuits. You're going to need some practice. Make sure to do that. Okay, cool? Okay, cool.